Hi everybody. I'm sorry for not being there today, but I'm hoping that I can walk you through the homework. So I know the substitutes there, and I'm gonna tell you when to pause things, especially when there are some opportunities for some boneheaded moves here. So we've got a couple of different problems. This was page 71, I believe. Numbers 8, 9, and 10. So number 8 is about a Mexican jumping bean. Number 9 is about a pig on a hill, and number 10 is about the Apollo moon landing. So let's start off with number 8. With B period, I know we sort of got a little bit through this, but I just want to sort of take you all the way through it, and then D period, this is sort of where we left off. So why don't we take a look at this? We're dealing with a Mexican jumping bean. Jumps with the aid of a small worm that lives inside the bean. So if the bean has a mass of 2 grams and jumps 1 centimeter from your hand into the air, how much potential energy is gained after it reaches the highest point? And B, what is the speed as the bean lands in the back in the palm of your hand? Yeah, I can talk. So I guess the first thing I need to call your attention to are the fact that we've got 2 grams and 1 centimeter. And my B period, I called attention to this, but I'm not sure if I did it with D period. So you need to convert the grams into grams into kilograms and centimeters into meters to even think about doing this. So why don't you pause it here, so that we can take care of doing that conversion. If my students haven't done it, give them a couple of seconds to do it. So pause it here. And so you should have ended up with the mass of this thing is 0.002 kilograms. 0.002 kilograms. And the height is now 0.01 meters. And again, this is 2 grams times 1 kilogram over 1,000 grams, and that will equal 0.002 grams. And the meters is going to be 1 centimeter times 1 meter over 100 centimeters. Centimeters cancel out, and you're left with an answer of meters of 0.01 meters. So anyway, that's sort of the big important piece. So now you've got, forgive my drawing here, you've got a hand, or a tree branch. But you got a hand and a Mexican jumping bean right there. And the Mexican jumping bean can jump 1 meter up and back down. And we're looking for the change in potential energy. So how much potential energy does this thing gain? So delta PE equals mg delta H, mass times gravity times the change in height, which would be 0.002 kilograms times 9.8 is my gravity, times the change in height, which is 0.01 meters. And on a good day, I have my handy dandy calculator here. This is Blue's Clues. 0.002 times 9.8 times 0.01. You should end up with 0.000196 joules of energy. So that should be the change in potential energy. And then the question is, well, if that's how much it gains when it goes up, so the beam comes up, how much kinetic energy basically does it have when it comes back down? That's why they're asking what's the speed. So we know that this is the potential energy that it gains as it flies up. And this potential energy is going to turn back to kinetic energy as it comes back down. So we can basically make the assumption that 0.000196 joules is also going to be my kinetic energy, which is also equal to 1/2 mv squared. 0.00196. So what we can do is multiply both sides by 2. Those will cancel. My mass hasn't changed. It's still the bean. So it's 0.002 kilograms. So it's going to be, let's see, times 2. So 0.0002 392 equals 0.002 v squared. So I just got rid of the 2 and multiplied through by the 2. I'm sorry, I got rid of the half and multiplied both sides by 2. Now I'm going to divide both sides by 0.002. That's going to be my v squared. So divide by 0.002. That's going to be 0.196, and we'll take the square root of both sides. And that should be a velocity of 0.44 meters per second. So I hope you got that, and if you didn't, I hope you get it now. I'm gonna have I'm gonna give an opportunity to pause, and I want you guys to compare notes with the people around you for maybe 30 seconds. And if I screwed up or if you screwed up, why don't you talk to the person next to you about what happened? So we'll pause it. And let's get on with the second problem here. So let's go to number 2. A 500 kilogram pig is standing at the top of a muddy hill on a rainy day. The hill is 100 meters long with a vertical drop of 30 meters. The pig slips and begins to slide down the hill. What's the pig's speed at the bottom of the hill? Use conservation of energy. So we're going to use the conservation of energy, which states PE initial plus kinetic energy initial equals potential energy final plus kinetic energy final. And the beauty of this is he's standing at the top of the hill, which means in the initial, all of the energy he's got is potential. So if he's standing, there's no kinetic energy because he's not moving. And at the bottom of the hill, there is no potential energy because the pig is basically moving. And that's it. So we get to get rid of the kinetic energy in the beginning and the potential energy at the end because, again, in the beginning, there's no kinetic energy. And at the end, there's no potential energy. So from here, it just becomes basically plugging and chugging. mgh equals 1/2 mv squared. And all we have to do is do some plugging in. Now the question is, the hill is 100 meters long and it's got a vertical drop of 30 meters. So we have to make a decision. Do we use 100 for the h or do we use 30 for the h? And here's a picture of a hill, not to scale. 30 meters, 100 meters. Which one's the height? Ask your partner. Pause. So, which one's the height? 30 meters. 100 isn't the height. I didn't ask you to measure how long the stairs were when you were running up and down the stairs last week. I asked you to measure how high the stairs were. Because all we care about is the height. So this really becomes a true plug and chug. 500 kilograms times the gravity, 9.8, times the height, which is 30, equals 1/2, times the mass, which is 500, times v squared. And the beauty of this is you can cancel out the 500s because they're on both sides. So it really just becomes 9.8 times 30. So that's going to give us 294 equals 1/2 v squared. And we're going to get rid of that 1/2 by multiplying both sides by 2 times 2. And we're going to end up with 588. 588 equals v squared. And then we all know the next thing to do is you take the square root of both sides. So square root of 588. We should end up with a poor pig going down the bottom of the hill with a velocity of 24.24 meters per second. And that's going to be really, really fast because that's about 50 miles an hour. That poor pig. Can you say bacon? My sense of humor is terrible even though I'm not there. Okay, I hope that made sense. Again, why don't you take a couple of seconds, talk to the person next to you, make sure everything makes sense before we move on. And when the class is ready to move on, hit play again. So why don't we pause it here? And I'm going to move on to number 3. So while on the moon, the Apollo astronauts enjoyed the effects of gravity much smaller than that on Earth. If Neil Armstrong jumped to the moon with an initial speed of 1.51 meters per second to a height of 0.7 meters, what amount of gravitational acceleration did he experience? So here's the crazy thing. We are going to be solving for g. And you might ask me, how would we do that? And we're going to use the law of conservation of energy. And I totally understand if you didn't get very far in this. So I'm going to try and walk you through it, or I'll get you to a point, and then I'm going to have a pause, and let's see if we get up to the same answer, okay? But the law of conservation of energy one more time states that PE plus KE initial equals PE final plus kinetic energy final. And this shouldn't be news yet. This should be old hat, because we learned this, a week and a half ago or so. The way you need to think about this is, and forgive me, but there's the moon. Let's get the crater over here, and here's Neil Armstrong. Yeah, just go with it. So he's on the moon's surface, and if he's on the moon's surface, before he jumps up, he's got a potential energy of 0, because he's on the ground. And he jumps up with kinetic energy. So he's got an initial speed of 1.51 meters per second. So we can use that. We know kinetic energy is 1/2 m times v, which we know is 1.51 squared, mv squared, 1/2 mv squared, equals the potential energy final plus the kinetic energy final. So we know the potential energy is mgh, plus, when he gets up to the top, how much kinetic energy does he have? I hope we realize that, just like with kinematics, at the top of your path you have a velocity of 0. And if his velocity is 0, his kinetic energy is 0 joules. So we can kind of nuke that. So we can kind of look back at this and say, all right, let's just rewrite this. I'm going to copy it down. 1/2 m times 1.51 squared equals mgh. Well, they don't give us his mass in here. It could be 100 kilograms, it could be 1,000 kilograms. I don't know how heavy Neil Armstrong was. But let's be honest here, we got a mass on both sides of the equation. And just like with the pig question, I could get rid of the 500 grams of the pig, I can get rid of the variable m on both sides. Just dividing by both sides by m. So now I'm stuck with 1/2 times 1.51 squared equals g times the height. Remember, I'm looking for g because we're looking for the gravitational acceleration. I hope they give me a height. And I hope that you see here, they do give us a height. So why don't you pause it here and let's see if we can get to the same answer. I'll give you a second to pause it and then come back to me. So if we do this correctly, 1.51 squared is going to be 1/2 times 2.2801, which I'm going to drop, equals g times my height, which is 0.7. So 1/2 times this equals g times 0.7. So if I divide both sides by 0.7, those cancel, and now I'm left with g is going to equal whatever all this is. So I'm going to do some multiplication. 0.5 times 2.28 equals blah blah blah, 1.14 divided by 0.7, which is 1.62 meters per second squared. And that is what we solve g to be on the moon. And now I'm going to consult the Google. Okay, Google, what is the acceleration due to gravity on the moon? Can we be patient?
1.620 meters per square second. According to soft schools, the acceleration due to gravity on the surface of the moon is 1.620 meters per square second.
The Google doesn't lie. So I hope you got that, and I hope that if you didn't get that, take a second and talk to your compatriots next to you. And then why don't we can look at the next set of questions for you. Oh, yes, energy student, that's you guys. So what I'm going to have you do from here on out is, and I know that you can see my screen, which is nice. We did that, we've done that, we did these, we did all of this, all of this, all of this. We get to skip all this. I'm actually going to have you guys work on, this is all mechanical advantage and stuff. I'm going to have you work on questions A1 through A10. A9 and A10 are kind of tricky, but I think you can handle it, and if you can't, we'll hit them again in school on Wednesday. So, and if you don't have them, they should be up at the front of the room, and if they're not at the front of the room, hopefully your friend's got one. You can just copy down the questions. So good luck, and I will see you all on Wednesday. I hope this helped. Bye bye.